Can everybody hear me okay? I guess that looks pretty. I never used one of these before, so this is new for me. So let me put this in here.
I think it's working.
Okay, great. And let me make sure I have enough intelligence to operate the. Okay, this is good. Major point. Okay, great. So thank you, Gaiman. My name is Dan Arnold. I'm a fourth-year PhD student in mechanical engineering, and I'm here to talk to you today about software for the smart grid in the home. So I'm a mechanical engineer. My background is in controls, and I work in software. So I gave a talk at a conference in San Diego this summer, and somebody came up to me after and said, I'm having an identity crisis because I don't know who I am or what I'm doing. And the fun thing is that they're probably right. So anyway, so our work is titled Reference Design for Residential Energy Gateways. It's sponsored by the California Energy Commission's PEER program and the California Institute for Energy and the Environment, and the PI is Dr. Dave Auslander in mechanical engineering. So today in our brief 20 minutes or so, I'm going to give you some background and motivation about why the situation in the residential smart grid necessitates the development of some sort of open source gateway reference design. We're going to talk about the current progress in our reference design to date, a little bit about what our plans are for the future, and what issues do we have to address to meet the objectives which we outline in our current plans. So just out of curiosity, when I was putting this presentation together, I Googled residential smart grid to kind of get a feel for what society thinks the smart grid can offer consumers in the home. And so I think this is a very illustrative picture that kind of shows really the future, the vision, the end game, if you will. So we could all live in a home. Of course, we all have our solar panels. We're all generating our own electricity, perhaps. We have appliances that are networked, denoted by these circles things here. We have our HVAC system also connected. So the idea here is around networking. We're trying to bring together these elements which historically have not had the ability to communicate, and now they can communicate. And there's also some connection between the home and the outside world. So let's zoom in on this a little bit and take a look at the smart grid elements themselves. So we have here some washer, dryer, smart appliances which presumably have the ability to respond to some external signal, maybe communicate their energy consumption. Of course, an essential element of the smart grid is the smart meter, currently deployed in many homes in California. A very popular area of research these days is the integration of plug-in electric vehicles. This would become another part of the residential smart grid. And then we have these other devices, which are kind of intermediary devices. This is a gateway here, the function of which is not so clear as these guys, but is really meant to kind of bring together communication, facilitate kind of this whole network in the home. So everything looks pretty good at first glance, but if you look a little closer, you can see that there are some dissimilarities outside of just, oh, this is a wall outlet and this is a PCT. So on closer inspection, you can see that there are different standards for communication which exist in the residential smart grid. This smart wall outlet here communicates over Z-Wave. This one here, this ecobee smart thermostat, which I've tried to highlight, that little symbol there is like the Wi-Fi symbol on your laptop. So this one communicates over Wi-Fi. And those of us who work in this space are very familiar with the Zigbee Alliance stamp of approval for devices which they incorporate into their smart energy profiles. And this is some device which is displaying the price of energy. So to summarize, the home area network, within the home area network, multiple communications media exist. You have Wi-Fi, Zigbee, various flavors of SEP perhaps, Z-Wave, and you even have some hardware standards, hardware interfacing standards, USNAP, which are showing up also. In addition, you have different data models for the exchange of information in these networks. Some are based on XML or JSON. SEP utilizes clusters to kind of organize their data. Some of these are proprietary. So what this really means is that, by and large, there's a lack of interoperability, widespread interoperability for home area network smart grid products. And this is kind of where we come in. What can be done to remedy the situation? Well, some sort of intermediary device could theoretically facilitate the interoperation at the application layer between these different standards. A modular architecture seems like a good idea. You can plug and play different elements without compromising the integrity of the system as a whole. We could provide a single mechanism to exchange information, to exchange information with the resident, and provide them with kind of a picture of how the whole home area network is operating, rather than having multiple interfaces, one for each network, and the guy has to run around from upstairs to downstairs to address all the different networks individually. Furthermore, an open source reference design could help encourage some sort of de facto standardization, and this is really what we're hoping our design will do. So just a diagram of how our residential energy gateway would communicate with physical entities in the home area network. Clearly, within the home, the gateway is the coordinator for all energy-related information exchange. It's also the mechanism by which information is exchanged with elements in the outside world, with the exception of the electric utilities back end to your smart meter. So the gateway could talk to things like a resident user interface, any appliances you have that are capable of communicating, your HVAC system, any local generation you might have, and of course a smart meter. And when communicating with elements outside of the home area network, it could talk to things like a demand response center, other gateways, an aggregator, and perhaps your electric utility. Just to illustrate rather simplistically how the gateway would speak multiple languages, if you will, or be able to communicate over multiple communication standards. Pretty self-explanatory. We even leave the realm open for another standard should it emerge sometime down the road. So what have we been doing in the past 3 years? We began this project in 2009 in July. We've recently had our funding extended to the end of next September 2013. We've chosen to develop our reference design to be targeted for a netbook or a laptop, something very small, to kind of enforce the constraint that we want to have very modest computation in our software, and hopefully that will translate into a cheaper price for the consumer if these things eventually go to market. We support communications protocols based on Wi-Fi Ethernet, Zigbee Pro, generic Zigbee Pro, and SSH. Our data models are currently based in XML and JSON. We are programming the gateway in Java, and a large reason we chose Java was for the presence of this really interesting and very cool software architecture known as Open Services Gateway Initiative, OSGI. If you just Google OSGI, there's a lot of information about it out there. What it really does is encourage high levels of modularity and interoperability when you're programming an application, a software application, by enforcing that you write your code, your jar files, into these little bundles. And if you kind of follow their blueprint, you can plug and play these bundles with relative ease. And that's the framework within which we've written our system. So beyond the specifics, what have we been able to do with this so far? What can the system do today? We've been able to integrate an external demand response resource into the gateway, and this is accomplished, the signal is an open ADR. We get it from an Akuacom demand response server via the web. We've developed a dynamic web interface to allow the resident to customize their response to a demand response event, and also to have supervisory control over any connected appliances in the home area network. Putting all this together, the gateway we've shown we have the ability to actuate physical appliances in response to some external demand response signal. And a few milestones, just one this summer. We had a paper presented at IEEE Power and Energy Society in San Diego, and this project was the winner of the 2011 Dow Sustainability Innovation Student Challenge. So pretty cool. The response from industry has been very, very positive. And this is kind of culminated with the emergence of ST Microelectronics as an industry partner. For this project, they donated engineering hours and several single-board computers, and they're interested to see if we can port our software onto their hardware and to see if we can use that in our demand response plug load testing. An illustration of how the gateway is actuating both simulated and real appliances. We communicate with simulated appliances, which are housed on separate laptops. We use Wi-Fi for that, denoted by this Linksys router. We communicate with simulated appliances over a generic Zigbee Pro network, accomplished with these Telegesis USB dongles. We plug one into each computer, and we can communicate over Zigbee Pro. We communicate with real appliances via an intermediary device, this Raritan power distribution unit. It's essentially a smart power strip. You can independently meter and actuate all of the ports on the front of this device. Interestingly enough, we've actually obtained other manifestations of this PDU, not from the Raritan, but those that communicate over Wi-Fi. So we're going to be trying to integrate other physical plug load control devices in the very near future. Physical implementations. This technology, if you stick around this afternoon, you're going to get to see it in action because we've deployed it to manage plug loads as part of the DI80R project, Deep Building Demand Response. And there's going to be a demo of this software this afternoon upstairs. I think it's in room 456. In addition, we're going to be deploying our gateway to manage a suite of dormitories at the U.S. Air Force Academy sometime this fall. So another fun thing on the horizon. This is a picture of the gateway with some elements it's controlling on our old office upstairs, so just down the hall. The gateway, which we call the EIG, Energy Information Gateway, in this context is housed on a desktop computer. We can communicate with Wi-Fi appliances and Zigbee appliances via those respective standards. They're housed on laptops here. The web interface, the user can come in and tailor their response to a demand response event and also view the status of all connected appliances. And the user, we communicate with physical appliances, this desktop fan and this desk lamp via the use of this Raritan, which is shown in the lower left corner. So we've had a lot of success in the past few years, but there's still a lot we'd like to do. So far, the connection to the smart meter has been a bit elusive due to the lack of available hardware that allows us access to, at the application layer, to Zigbee SEP 1.0 to communicate with that hand radio in the smart meter. But we've identified some products which might fit the bill and allow us to do this. So there's hope. We'd like to continue to integrate dissimilar products, dissimilar physical products into the gateway sphere of influence. So in addition to the Raritan I mentioned before, there are other smart power strips out there, smart devices that have an open enough API that we could integrate it into our system. So we're planning to do that as well. Perhaps most importantly, we really love to integrate the gateway with some existing standard which you'd find in the smart grid, in the residence, in the residential home area network. And this includes things like Z-Wave and whatever flavor of Zigbee SEP you can get your hands on. The bottom line is the next version of the gateway is meant to address these issues. So expanding on the third item on the last slide, how are we going to do this? How are we going to integrate these multiple communication standards? There's a lot of complexity here. Each standard has its own data structure. We need to account for the possibility of multiple standards existing in the home area network. Somebody could have some of his home area network be Z-Wave, some of it could be Zigbee, some of it could be Wi-Fi. But we'd still like to have a single interface for the resident to be able to interact with each distinct hand network. In addition, it's also possible that these networks can intermingle. And by this I mean that you could have, for instance, some Z-Wave power strip in series with a Zigbee smart appliance. And this creates some interesting issues for control because now if you want to actuate this smart power strip, you're going to lose the ability to control that smart appliance, this Zigbee smart appliance. So we have to kind of think about these relationships, how they're structured in the code, and how we make the resident aware of what the systemic effect of their actions are going to be. So now we're going to identify some important issues we have to consider in order to kind of meet these objectives and the objectives on the previous slide. So the first important issue I just elaborated on is the hierarchy of devices is very important. The example I just gave, you could have a power strip, which is the parent of two smart appliances, maybe your TV and your set-top box. You might not want to turn off this power strip if you knew the effect was going to be you couldn't watch TV for the duration of a demand response event. So it's important to realize that controlling the parent device would affect the children. How do we communicate this relationship to the occupant in something that's meaningful and easily visible to them via like a web interface? How do we define these associations in software? Another open issue we have to consider. Another outstanding issue which we're looking at is the evolution of these data schemas, which either comprise the format of information exchange in the networking standards themselves, but also for our own internal gateway data structure, it's desired to have something based on an open standard, something people can see what the structure is. And here I've shown an XML schema And it's very commonplace for networking protocols to base information exchange on XML schemas here. But the issue is that somebody could come in and put a new element in here. And we'd like to be able to react to that without destabilizing the system, without doing like a firmware upgrade or a patch or something like that. So we need to think about how the gateway would handle a new element being introduced either into its data structure or into one of the networks with which it's connected. How are these new schemas integrated into the system? And what happens to data that was validated against an older schema? We need this to be a very stable operation without any crashes or errors being thrown when we upgrade to a new schema. The last important issue which we've identified so far is, I mentioned briefly before, is the notion of an internal data structure for the gateway. And to borrow a little bit of mathematics from set theory, if we define the data set, the data structure, the data schema of the gateway by this G, we can define one for ZigBee, any ZigBee you want, Z, and one for Z-Wave W. If we make the gateway's data schema structure a superset of both ZigBee and Z-Wave, then what we can do is we can define mappings from ZigBee into the gateway and from Z-Wave into the gateway without losing any kind of specificity of information. Everything would be preserved, albeit in a new form, in the gateway's internal data structure. An interesting side effect of this is that now we can invert one of these mappings, and we now have the ability to map signals or information from one standard, an element of Z-Wave, into another standard, an element of ZigBee. And what this really means is that some device from a ZigBee SCP 2.0 network could now perhaps view the rest of the home area network as a virtualized SCP 2.0 network. So now you could have some display here which sees all of the elements in ZigBee in this network, but also views any kind of smart appliance that's communicating natively over Z-Wave as some virtual device. And this is something that I've really kind of yet to see addressed for networking in the home area network thus far. So we do have a plan to address these issues, to incorporate them into our reference design. With regard to device hierarchy, we're planning to use this another off-the-shelf product of Java, which has some very powerful features. This Java naming and directory interface, JNDI, to establish parent-child relationships between the different devices connected to our system. In order to address item number 2, the data schema evolution, we're obviously not going to hard code any of our schemas physically into Java. It makes much more sense to utilize some sort of dynamic schema binding where we can use this schema as the mapping itself to change information from whatever proprietary thing is going on in your network into the gateway's data structure. And we can do this at runtime with the tools in Java, which is very cool. With regard to the gateway's data structure itself, we're going to clearly define mappings via XML. What's very nice is that a lot of standards, SCP 2.0, for example, already does this. They already have published their schemas for information transfer for different smart grid elements. And then Java would then use these XML files for object-to-object mappings. And that's it. So if you're interested, please visit our website for more information. And just thanks to everybody for making this project possible so far.
Oh, thank you, Dan. Again, we have a couple of minutes for questions.
This issue of connecting different devices in homes is the same issue in every kind of a building. The one area that seems to be able to, that we think there's some promise in, is integrating the information that's already being generated by the manufacturer's devices themselves. Most of the manufacturers today have intelligent devices that are used to maintain themselves for operation. They don't get too hot, they don't get too cold, they don't run too long. In fact, you can see if a service provider comes in to take a look at your washer, your dryer, your refrigerator, they don't use the old tools they used to use. They just plug into it and it tells them what's going on. Now, most of that information is used to make sure they operate properly. But that information also could be used for energy efficiency, demand response, optimization, interactions, transactions, arbitrage, whatever you want.
Mm-hmm.
What have you had any success in working with these manufacturers to find out what kind of information they would be willing to share, how they would share it in a more intelligent way, so they're not just transmitting raw data like temperature, flow, pressure?
Yeah, so a lot of that depends on the context of the manufacturer, obviously. The one party we've been involved with talking to, and this issue did come up, was Technicolor out in Paris, who make the equivalent of our Comcast set-top boxes. And they are exploring the notion of putting a software like this onto their set-top box and utilizing that extra flow of information to bring something else into the home area network. So that's definitely a possibility. The use of it in other contexts, specifically when you're not physically co-located with the device, is going to depend on the openness and the willingness of the manufacturer to kind of give us access to that data, if we can even get it over something that's wireless or wired.
Okay. How are you addressing the privacy and security considerations, since the gateway is not just interoperability between standards within the home, but also a gateway outside to third parties?
That is an excellent question, and that is on the mind of everybody who works in this space. I guess this slide will do. So the idea with merging these things at the application layer was that we could find some component, some dongle, to plug into our laptops, which is inherently secure. So this path of information here is already secure. The idea is to do that with all of the other networks we have connected to the gateway. OSGI does also provide some inherent security in the form of a key exchange for bundles to interact with one another. So there is the mechanism to support also security within the gateway itself. This is a hard issue to tackle because the security of every standard is different, and the standard which evokes the most passion about security is Zigbee SCP 2.0, which is kind of yet to really materialize. So it's been a difficult road so far, but we are aware of these significant challenges. But so I just want to say, so far, we're focused on interoperability of the different standards, but we're not pushing the idea of security out the door.
Okay, we have one more question.
Actually, I have two questions.
Okay.
It's Marianne Piet. I have a question about price points, because we know that the price point to bring technology like this into the home is a real challenge. Mm-hmm. And if you could comment anything about the price points. And then my second question is application to small commercial. Okay, great. And in small commercial, I'll just say, certainly my guess is you'd want some backnet interoperability. But if you could comment on those. Sure.
So let's start with the second one first. So how do we kind of deploy, or how would we deploy this in a small commercial environment? Well, so we've actually already done that. We've deployed this system to manage plug loads in the office of stairs. And we've developed a connection to another piece of code, like a central building controller, that does communicate over backnet. So what's nice about the modularity of the gateway, organizing it in OSGI, is that the gateway is just a collection of these bundles. And we can take the ones that we want to whatever application we need. So the only real difference between the residence and a light commercial space right now is the lack of the smart meter there. And now you have this connection to the building manager, some building central controller. So we're able to utilize largely almost the same code base in both areas, which is why this product we've been able to successfully develop it for the residents, but apply it in the commercial setting here. With regard to price points, this is something that our industry partner, ST Micro, is extremely sensitive to. And I don't remember what their price point was that they were trying. I mean, clearly under $100, I think, is what they're trying to get these things to sell for. And they are interested in once our software is proven on their product, to have a version of it running with silicon that they make for all the radios, Wi-Fi, Zigbee, to be produced in-house to keep prices low. But I think off the top of my head, they were aiming for something under $100.